welcome to the class by Ravindra Babu Ravula. So today I am going to discuss theory of computation, TOC. And before starting the class, I would like to tell you a few points. First of all, this class is only about GET. So I am not going to discuss all possible theorems, all possible proofs and conjectures. I'll be discussing mainly about GET. So the main intention of this class is to help you in answering all the GET questions. So I'll be mostly interested in discussing the techniques and maybe some important methods using which you'll be able to answer all the GET questions. I'm not going to discuss all the proofs, all the theorems, all the conjectures. That is the first important point. And the second important point, when you are watching this video, if you don't understand anything, you can stop it there, go back and listen to the point again and come back to the next topic, right? And I will even give you some time to take down the notes. Even if I didn't give you any time to take down the notes, you can just pause the video, write the important points, or maybe take a detailed notes and then continue. And even if you don't understand some few problems when I'm teaching, don't worry, just go through the complete video, maybe finish off the entire subject. Definitely you will understand everything by the end. So if you don't understand anything at any point, don't worry, just finish off the video. We shall you can again view the video and then you can understand it. Okay, so let me start the subject. Today I am going to discuss TOC, theory of computation. T means theory, O means of, C means computation. So by this name you must be understanding that this is something about computation. So what is computation? Computation is nothing but any task that can be performed by a calculator or a computer. So we are going to mathematically model a computer or any machine in general, and then we are going to study the theory about it, which means what are the capabilities of this machine, what are the problems that could be solved by this machine, and what are the limitations of such a machine. Okay, so the basics of this subject are, I'm going to discuss all the basics now, right? First of all, the basics of the symbol is, the basic of the subject is a symbol. What is a symbol? Symbol is the basic building block in this subject of TOC, and a symbol can be any letter like this or anything. Even you can have pics. This is a symbol. From a symbol we can form alphabet. This is generally represented by sigma. Sigma is also called as alphabet. So the alphabet is nothing but some collection of these symbols. For example, A comma B. Now once if you define the alphabet, all the strings, okay, what is a string? I am going to discuss it. Everything will be based on this set, this predefined set called alphabet. So you can have any number of alphabet, any number of symbols in the alphabet. In this sense, you can even have ABC, or you can even have 0, 1, or you can even have 0, 1 to 9. It is a finite set and it can be anything. Okay, and from the alphabet we are going to discuss a string. A string is a sequence of the symbols, which is nothing but, example is, let us say A. If alphabet is A comma B, small a is a string over this alphabet which is of length 1, and small b is also a string of alphabet which is of length 1, and AA is also a string of the alphabet which is of length 2, AB, BC, so on. So maybe if you consider this alphabet, some of the interesting questions are, how many strings of length n are possible over this alphabet? How many strings of length 2 are possible over this alphabet? length 2. Okay, so you can say AA, AB, BA, BB, which means 4. Now I am asking you how many strings of length n are possible. Length n are possible. We have n blank spaces and we have two options to fill in with, right? So what are the two options? Either A or B, either A or B, so on, which means 2 into 2 into 2 into so on n times, so which is 2 power n. So in fact you can even extend this concept to any alphabet. Since we have only two symbols in this alphabet, we have got 2 power n. So in general, if you have n symbols, or let us say the number of sigmas in this sigma, if they are represented by mod sigma, then the number of strings of length n possible over sigma is sigma power n. Sigma power n. So just think about, just revise what we have seen till now. First thing is symbol. What is a symbol? Symbol is the smallest building block in TOC, and if you take few symbols, we can form an alphabet. Once we have defined an alphabet, we are going to form strings using only the symbols in that alphabet. So symbol, alphabet and string. Okay, now using this I am going to define few more things. Next thing is language. Language. What is a language? So we know what a string is. Even if you consider English language is nothing but collection of words, isn't it? So in TOC, a language is nothing but collection of strings, isn't it? So for example, let us say sigma equal to A comma B. Then languages can be defined like this. Language L1 equal to, you can represent it say set of all strings of length 2. So using this alphabet sigma, what are set of all strings of length 2 we can form? So definitely the set is going to be AA, AB, BA, BB. So if you can check it, if sigma is A comma B, then the set of all strings of length 2 is nothing but AA, AB, so on 4. And in fact this set is a finite set, so I can call that L1 is a finite language. Okay, so let us define one more language, L2. Let us say L2 is set of all strings of length maybe 3, set of all strings of length 3 over the same alphabet sigma equal to A comma B. Then L2 is going to be A, B, A, B, A, B, 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 A, B, 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 A, B, B. Right? So there are 8 strings. Again this L2 is also finite. Let us say L3. L3 is, let's define it like this, set of all strings over the same alphabet sigma equal to A comma B, where each string starts with A. So that equal to, I am interested in set of all strings where each string should start with A. So the smallest string which starts with A is small a, right? And the next biggest string which starts with A is either AA or AB. And the next string which starts with A, see, starting with A, starting with A, starting with A. And the next string which starts with A is A followed by AA, or A followed by AB, or A followed by BA, or A followed by BB, so on, so on. So if you look at this language L3, L3 is infinite. If you look at these languages L1 and L2, they are finite. So now you have seen that a language which can be formed over a sigma, which can be formed over a alphabet, can be finite or infinite. Okay, please make a note of this. Fine. I'll be moving on to the next topic. Powers of sigma. So first thing is sigma power 1. So if, let us say, we have defined sigma as a comma b, which means our input alphabet contains only two symbols, small a and small b, only two symbols. Now sigma power 1, sigma power 1 is nothing but set of all strings which can be formed over a comma b, which are of length exactly 1. Again, sigma power 1 is set of all strings over sigma of length exactly 1, exactly 1. Okay, so they are simply A and B. So we can extend this definition as sigma square. Sigma square equal to sigma concatenated with sigma, that is nothing but a comma b concatenated with a comma b, that equal to, so how can I concatenate these two sets is 1, a concatenated with a is a concatenated with b is a b, b concatenated with a is b a, b concatenated with b is b b. Set of all strings, and all these strings are always formed over the same alphabet, so I am not going to mention it. All these strings of length 2. Okay, and the next one is sigma cube. So as you might have guessed by now, sigma cube is nothing but all the strings of length 3, and there will be exactly, and if you look at it, the sigma cube is set of all strings of length 3, and the cardinality of this set is going to be 8, so on. Sigma power n. Sigma power n is set of all strings of length n, which is nothing but n length strings. N length strings. So let us say sigma power 0. Sigma power 0 is set of all strings of length 0. Set of all strings of length 0. So the smallest string which is of length 0 is sigma power 0 contains a special symbol called epsilon. So it is also called as a null string, and I'm going to use epsilon, this symbol, to represent a string of length 0. This is a special symbol. This one is a special symbol of length 0. So just remember that epsilon is a special symbol of length 0, and I can even write it like this: length of epsilon is 0, and everything else is same, right? So string is, you have to you have to just see the number of symbols and then you can say the length of the string. But only for epsilon, just remember that the length of epsilon is 0. Okay, so if you want to make a note of it, please do it. I'll be moving on to the next topic. Next important concept is sigma star. So sigma star is nothing but, in place of star you can substitute any number starting from 0. Again, in place of star you can substitute any number starting from 0. So sigma power star is sigma power 0 union sigma power 1 union sigma power 2, so on. So what is sigma power 0? As you know, sigma power 0 is simply 0. Let us define sigma first. Sigma for this question is a comma b, and the sigma can change from question to question. Okay, so in this question, for sigma star, it is going to be, sigma power 0 is going to be epsilon union, sigma power 1 is going to be a comma b union, sigma power 2 is going to be aa, ab, ba, bb, so on. Finite or infinite? Obviously it is infinite. And if you see this, maybe by looking at this definition or by looking at these sets, you can conclude that sigma star is nothing but set of all strings possible over a comma b, which means set of all strings possible over a comma b of all lengths. So maybe you can call it as the mother of all languages, or maybe you can call it as the universal set. So sigma star contains all possible strings possible over a comma b. Sigma star contains everything that includes a comma b. Finite or infinite? Obviously it is infinite. Okay, so this is about sigma star. Once we define sigma and sigma star, next thing is we can define a language. So we have already seen that language L1, L2 and L3 previously are nothing but sets of strings. L1 and L2 are finite and L3 was infinite. I mean, in the previous example, if you can remember it. So we have already seen that there are some finite languages and there are some infinite languages. Now you can see this, either this L1 or L2 or L3 are actually parts are present in this. So I can even write it like this. So L1 is actually a subset of sigma star, L2 is also a subset of sigma star, and L3 is also a subset of sigma star. Okay, so now we have languages. We have sigma, which is alphabet, we have sigma star, which is set of all strings possible over the alphabet, and then we have chosen some subsets which are nothing but the languages. So a language is nothing but any subset. It can be finite or infinite, which you should be able to define precisely. And these are all the languages possible over sigma star. There are how many languages are possible over sigma star? Infinite. Number of strings possible over sigma is infinite, and the number of languages that are possible over sigma star are infinite. And now the question is, why are we discussing about strings and why are we discussing about languages? Where are we going to use it in practice? There are many applications, there are many practical applications, but I would like to take just one example and tell you where we are going to use them at practice. Okay, so you can consider the C programming language. Let us assume we have the language, the C programming language. Okay, if you look at the C programming language, what are the symbols that we type when we are writing a program? Maybe you type the symbols like this: small a, small b, so on, small z, capital A, capital B, so on, capital Z, 0, 1, so on, 9, and some special symbols like plus, star, so on. So this is a finite set. We are going to always use a finite number of symbols in order to represent a C program, in order to type a C program. And now you can call this as sigma for the C program. So the alphabet for any C program is going to be this. The alphabet for any C program is going to be this, which is obviously a finite. Always remember, alphabet is going to be finite. It is never going to be infinite. Okay. And next one is, using these strings or using these symbols, we are going to form a string, right? So if you write like this, void main something, and then int a comma b, so on, and close it, this is nothing but a string. This is actually a program in C. In C it is a program, but coming to TOC, it is nothing but a string, isn't it? Sigma is nothing but alphabet when you come to TOC, and is nothing but set of all symbols which are allowed when you look at C programming language. And now a program is nothing but a string. Interesting. Now the question is, what is C programming language? What is C programming language? C programming language is nothing but set of all valid programs. Set of all valid programs. So when I say, the important word is valid, which means there can even be invalid programs which will give you some error when you are going to compile it or when you try to run it. So the interesting question here is, what are the valid programs? And given any program, how can I say that the program is valid and the program is invalid, right? So first question is, how many strings will be there in the C programming language, or how many programs are possible over C programming language? Answer is infinite. You can write any number of valid C programs, like let us say P1 is a program, P2 is a program, P3 is a program, so on, infinite. So the C programming language is going to be infinite. Now the next question is, given a program Pn, given any program Pn, how can you say that it is valid? We can say that it is valid if the program is present in this set, in this language. Now the question is, how can I find out whether a given string is in the language or not? Or let's go to C programming language. How can you find out that a program is valid, and how can you find out that there are no errors in the program? So smallest thing, maybe the naive answer is, you can ask me to save set of all possible programs on a computer, and then just check if this program Pn is a part of that all the programs or not, which means that the smallest solution or the simplest solution we can think of is, save all these programs on the computer, and given a program, go on scanning programs one by one, and if there is a match, we can say that it is valid. But the problem with this is, any computer will have a finite memory, but then the number of programs possible is infinite. So obviously we cannot do this. So we are mainly interested in this. Given a language and a string. Now the interesting question I want to ask is whether this string is present in this language or not. If the language is finite, yes, you can enumerate all these strings in your memory, and then given a string, we can scan all these strings one by one, and we can check if this is present or not. But the problem is, if the language is infinite, obviously we cannot store all these strings in the language on a computer. Therefore, entire thing boils down to small point. I'm going to erase this, please make a note of it. So now the entire thing is going to boil down to this: if L is finite, let us say example is, if sigma equal to a comma b, let us say L1 equal to set of all strings of length 2, AA, AB, BA, BB. If this is the language, and if I give any string, let us say AAA, and if I ask a question whether this string is present in this language or not, you could take each string and then examine each string and then verify each string and then verify, and you can say that it is not there. Since the language is finite, you can do it. But what if the language is infinite? Let us say language L2 is set of all strings which are going to start with A. Then the language is A, AA, AAA, AB, so on. There are lots of strings, right? So if any string is given, let us say string given is B, A, B, A, and if I ask you whether this string is present in this language L2 or not, then the problem is, how long should I be comparing this? See, don't say that maybe by looking at the first symbol it is very clear that the string is not in the language. Yes, for us it is clear, but then for a machine it doesn't think this way, it doesn't think logically. You have to give it a method, right? So so if this language is infinite, if you use the method of linearly searching all these strings and then matching it against, then the language will take forever, or the machine will take forever to answer this question. So the simple thing is, how can you, given a language, come up with a finite representation and some finite representation which can be stored in the memory, using which if I give a string, now you should be able to say yes, this string is in the language, or no, this string is not in the language. Now for a language, I want a finite representation. Whatever you could do, I want to store it on a computer in a finite amount of memory and then execute on this using this, and given a string to this finite representation, I want to say whether this string is present in the language or it is not present in the language. That is the simplest thing. Okay, so maybe let's take an example and see what this finite representation could be. Okay, so I'm going to erase this, you can make a note of it. The finite language, see, what is the finite representation is the simplest or the smallest machine. It is also called as a machine. Okay, so let us say given a language, I will try to construct some finite representation which is called a finite automata, and then using this finite automata, if I give a string to this finite automata will say yes, I accept this string, no, I reject this string, which means this string is present in the language or this string is not present in the language. Before discussing about what a finite automata is and what are the types of finite automatas, I would like to take a small example and maybe we shall discuss the definitions later. Fine. So let us say I am drawing some finite representation for a language. L1 is a language which is set of all strings which starts with A. Then it is small a because A is going to start with A, AA, AB, AAA, so on. right? So I'm going to construct a diagram which I'm going to call it as finite automata, and then we shall discuss about the definition later. Don't worry about it, I'll discuss it. How did I design it and what are all these? We shall go step by step. Here I just wanted to make a point. So L1, even if you write it like this, infinite set, or if you use this finite representation, both are same. Now if this is the finite representation of this language, I can give any string to this finite representation, and now this finite representation, which is also called as a finite automata, in fact DFA, which I'll discuss later, will say yes or no. Let us name. So I'm going to call all these circles as states. All these circles as states. S-T-A-T-S, states. And in this case, we have states A, B, C. And whenever this circle is having a double circle like this, I call it as a final state. And whenever a circle is having an arrow to the left of it, which is not coming from anywhere, if I use this arrow which is not coming from anywhere, I just mean to represent that it is initial state. So initial state is A, final state is B. Now if I give me a string, if I take a string, for example A, B, let us say the string is A, B. Now my question is this: whether this string is present in this language or not. So don't just say that since it is going to start with A, obviously it is present. Yes, I know, but then I want to give this problem to a machine and I want to solve it. Therefore I cannot ask it to think intuitively or use its own logic. So using this machine, this finite representation, any machine should be able to answer this question. So how we are going to do it is, initially I'm going to write this string like this. Initially I'll be starting from initial state A. A is the initial state, and upon looking at small a, A is going to state B. And upon looking at this string or the symbol small a, B is staying in the same state. Upon looking at small b, B is staying in the same state. Now see this, upon scanning the entire string we started from the initial state and we are able to end up at final state. So a string is said to be in the language, or a string is said to be accepted by the finite automata if upon scanning the entire string we reach from initial state to final state. So this string is said to be accepted. Now maybe you can take the string B, A. Let's take that string BBA. Is this string in the language? No, right? Why? Because it is not going to start with B. So what should happen? This finite automata should say that this string is not in the language. So I am going to start in state A, and on seeing small b, I'll be going to state C, and I'll be in state C, and upon seeing small b, I'll remain in same state. See this, I'm going to be in capital C, and upon seeing small b, I'm going to remain in the same state. Therefore it is going to be C. And C on seeing small a, is going to remain in the same state. Okay, so you have to observe one point here. Upon looking at the entire string, or upon scanning the entire string, we started from initial state, and the last state C is actually not final. Here the state B is final, here the state C is not final. Therefore this string is not accepted by the finite automata, which is a means by which it is saying that the string is not in the language. So this string AAB is in the language, and the string BBA is definitely not in the language. So I have given you something about a finite automata. Now what is a finite automata, what are the various kinds of finite automata, what are the definitions, we shall look at them one by one. Maybe I'll take the simplest example, this one, and then I'll try to define everything. I'm going to erase this, maybe you can make a note of it. Okay, so the first thing is finite automata. Actually, automata is for plural and automaton is for singular, but then I'm going to use automata for everything. So the correct word is to use automaton, but then I'm used to using automata. So let's go with it. That doesn't make a lot of difference when you're solving gate questions. Okay. So finite automata are basically of two types. One is finite automata with output, and the other is finite automata without output. And again, finite automata with output is of two types. One is Murray machine, other is Mealy machine. Finite automata without output is of three types. One is DFA, other is NFA, and the other is epsilon NFA. Okay, so let's look at all these types. So we are going to look at all these finite automatas in detail. The first one I would like to start with is DFA. So DFA is nothing but deterministic finite automata. DFA is deterministic finite automata. NFA is non-deterministic finite automata. Epsilon NFA is non-deterministic finite automata with epsilon most. So we are going to discuss each one of them, but then I would like to start off with DFA. So first thing is DFA, deterministic finite automata. What is a deterministic finite automata? It's finite automata which contains Q, sigma, delta, Q naught and F. So generally any finite automata is represented by this quintuple. It is not just DFA, even you can represent DFA, NFA, epsilon NFA, all these, right, using this quintuple. I'll take an example and maybe I'll make it clear. Let us assume that this is some finite automata accepting some infinite language, some language A comma B, B, A comma B. This is A, B, C. Let us say B is the final state. Whenever I am writing this diagram, this is also a transition diagram. Whenever I am writing this diagram, I will use the arrow, this arrow, to represent the initial state, and I will use double circles to represent the final state, and the all the other states are simply some other states. Now in this, Q equal to set of all states. What are the states here? One is A, one is B, and other is C. And sigma equal to input small a comma small b, and Q naught, which is also known as start state, it is going to be A. See, I am writing all this for this particular DFA. Fine. And F is set of all final states, and in this case this final state is 1. So let's write what they are. Q is finite set of states. Sigma is input alphabet. Q naught is start state. F is set of final states. F is a set of final states. If you look at F, I am saying that it is a set, which means there can be a DFA with more than one final state, and that those final states are obviously one of the or a few of the states from all the set of states possible. So the relation between all these states and the final state is this. Q is superset of F. So this is how we can define all the elements of DFA except this delta. Till now, Q, sigma, Q naught, F, this is common for DFA or NFA or epsilon NFA. Only thing that varies or only thing that changes from finite automata to finite automata is delta. So let us say we have to define the delta. Delta is a transition function from Q cross sigma to Q. So what is Q? Set of all states. What is sigma? Input. So in this particular case, Q cross sigma is nothing but A, B, C cross A comma B. Therefore it is going to be Q cross sigma is going to be capital A small a, capital A small b, capital B small a, capital B small b, capital C small a, capital C small b. Fine. This is Q cross sigma, and now the Q is A comma B. There are only two elements. Now what do I mean by a function from Q cross sigma to Q is, see this, capital A on seeing small a, where is it leading? Capital A on seeing small a, it is going to capital B. Therefore I have to write this. And capital A on small b, where is it going? Capital A on small b, it is going to C. Oh, one more state has to be added. Capital A on small b is going to C, and capital B on small a is going to B. Capital B on small a is going to B. Capital B on small b is going to B. Capital C on small a is going to C, and state C on small b is going to C. So this is the transition function. So this is the definition of DFA. In DFA, for every state, for every input there will be exactly one transition, and this transition is exactly one, which means it is at least one and at most one. It is definitely one. So why is it called deterministic finite automata, or DFA? Is if you see any state, on seeing an input it is going to only one other state. If you consider NFA, on seeing an input A, it might even go to some other state, but in DFA, on seeing it small a, it is always going to go to one state. On seeing small b, it is always going to go to one state. So we don't have multiple edges with the same labels from the same state. So that is why it is called deterministic machine. And in computer science, deterministic machines are very important, because deterministic machines can be modeled, or even deterministic machines can be directly implemented as a software in computers. And the best example is in compiler design. Okay, so we shall take some example and construct a DFA. You could pause it and take a note of it. Now the question is, construct a DFA that accepts set of all strings over A comma B of length 2. So construct a DFA that accepts set of all strings over A comma B of length 2. It means that the input alphabet sigma equal to A comma B. First thing is identify the input alphabet, okay, and the second thing is you have to even identify the language. What is the language we are actually interested in? The language is set of all strings over A comma B of length 2. So what are all the strings of length 2? One is AA, other is AB, BA and BB. This is the basic steps, or it is the starting part. Once you identify that this is the language, take the smallest possible string. The smallest possible string is AA and construct the skeleton. Skeleton is nothing but on seeing small a, I'll go to some state, and on seeing one more small a, I'll accept it. Remember, before drawing any DFA, you have to draw the skeleton for the smallest string, and then we can build the muzzle over it. Okay, so now the thing is this a DFA? This is actually not a DFA, because if I see states capital A, capital B, capital C, capital A, you have given transition on what happens with small a, but then in capital A, what happens if you see small b? We didn't give any transition for small b, so it is not a complete DFA. Therefore, you just give one more transition on b. Okay, you just think about it. What happens if I see small b on capital A, which is nothing but if I see small b initially on capital A, then I need to accept it, right? And here also I am going to accept it. If you don't understand this, don't worry, we are going to do lot of questions. This diagram is exactly going to accept all the strings present in this language. Okay, so is this a complete DFA? Again, is this a DFA? This A is complete because on A you have given transition on small a and small b, which means A, if it looks at A or B, it is going to go to B, and on B you have given transitions on small a and small b, which means capital B, on looking at A or B, it is going to go to capital C. But what about capital C? For capital C we didn't give any transition. Now think about it. How did we reach capital C, and what happens if I see one more symbol in capital C? See, how did we reach capital C? We reach capital C by seeing either AA or AB or BA or BB. We have reached capital C by seeing AA or AB or BA or BB. Let's take any example. Let us say AA. If you are in capital A, on seeing small a, you will be reaching capital B, and if you are in capital B, on seeing small a, you will be reaching capital C, isn't it? Therefore, on seeing AA, we are going to reach C. Now if you are in C, if you get one more A, what does it mean? If you are in C and if you get one more state, one more symbol A, it means that we have seen a string of length 3. Is that string in this language? Definitely no. Therefore, if I see either A or even B, the string length is going to exceed 2. Therefore, I will be going to some other state D. Think about it. How did I reach C? Just by looking at any string of length 2, I am able to reach C. But then after the string of length 2, if I see small a or small b, it is actually going to be a string of length 3. Therefore, I am going to go to some other state. What if is this a complete DFA? This one is complete because on A or B you said what to do. and this one is complete because on A or B you said what to do. This one is complete because on A or B you said what to do, but then this one is not complete because you didn't decide about what happens on A or B. See this? Now let us say you are in D. So what does D indicate? D indicates set of all strings of length 3. If I get one more A or B, this is definitely set of all strings of length 4 and more. So anything after this I should not accept it, and I am going to be in this state. So how is this D acting is, once you reach D, it is never going to go back to final state. That is why I even call this state as a dead state or trap state. So you need not worry about the terminology about what is the dead state or trap state. Basically we have only two kinds of states. One is final, other is non-final. In this case, C is the final state or accepting state, and A, B and D are non-accepting states. In there is a special state. It is not anything special. I am calling D as a dead state because once we reach D, there is no way we can again come back and reach C. Okay, so if you look at this, C is accepting set of all strings of length 2, and if I get any string which is of length 3 or more than 3, I am going to reject it at D. Maybe we can take any example and you can trace it out. Let us say this string is A. I am going to start at A, and on looking at small a, I am going to go to state B, and on looking at small a in state B, I will be moving to C. So we have moved from initial state to final state upon scanning the entire string. Therefore I say that this string A is in the language. You can check it for all these strings. But if you give anything greater than this, let us say this string is A, B, B. Initially I will be in state A. On looking at small a, I will be moving to state capital B, and on looking at small b, from capital B I will be moving to capital C, and on looking at one more B, I will be moving to D. And upon looking at any number of strings of let us say A, we will be in D only, right? Therefore this is rejected, this is accepted, this is rejected. So now this is the time for us to define what is a string and how is it accepted by a finite automata. The definition goes like this: a string is said to be accepted by a finite automata if we are able to reach the final state starting from initial state upon scanning the entire string. Then the string is said to be accepted by the finite automata. Again, see this: a string is said to be accepted by a finite automata if upon scanning the entire string, if I can reach from initial state to final state, then I can say that a string is said to be accepted. If on scanning the entire string, if I am not able to reach the final state, if I end up in any of the other states, if I end up in D, or if I end up in D or B or A, then I say that string is said to be rejected. So this is the accepting state for this language, and these are the rejecting states or non-accepting states for this language. So there are two definitions. One is acceptance of a string, other is acceptance of a language. So maybe I'll write it down. It is worth noting down. So string acceptance. I say that a string is accepted by a finite automata if upon scanning the entire string, if I start from initial state and if I end up in the final state, then I say that the string is accepted by the finite automata. Okay. So it is like this: scan the entire string if we reach a final state from initial state. This is important, a final state, which means there can be more than one final state. At least if you are able to reach one final state, that is enough. Okay, so if you are able to reach the final state from initial state upon scanning the entire string, then we say that the string is accepted. Now the next one is, when do you say that a language is accepted? So a language is said to be accepted if we accept all the strings in the language. So language acceptance is a finite automata. It can be any finite automata. A finite automata is said to accept a language if all the strings in the language are accepted by the finite automata, as well as the strings which are not there in the language should be rejected by the finite automata. Okay, so a finite automata, it can be NFA, DFA or epsilon NFA, anything. A finite automata is said to accept a language if all the strings in the language are accepted. This is important. And all the strings not in the language are rejected. This is important. Okay, so you cannot say that a language is said to be accepted by a finite automata if it accepts all the strings in the language. The reason is, I can give you a simple automata which accepts everything. Okay, so just look at this. A finite automata should not just accept the language, or less should not accept all the strings in the language. It should also reject the strings which are not in the language. Maybe I'll just give you an example to clear this point. You please note it down. I'm going to erase it. So see this point. I can draw a small simple automata like this, and I can write it like this. This is the smallest automata. Give anything, it will accept. Give anything. For example, I can give, you can give small a. It will start from capital A, and on seeing small a, it is going to capital A. From initial state, we are able to reach the final state. Okay, before going to this, maybe you should get one doubt. What is this diagram? You are having the single state, and the same state is going to be initial as well as final. Do we allow such kind of automatas? Yes, it is perfectly legal. We can have the same state as initial state as well as final state, or even the initial state can be final state. Okay, so if you look at this diagram, I am starting from initial state, and on seeing small a, I am going to reach the final state. Therefore, A is accepted, and you give A. I'll start from A, I'll go to A, and again A. Initial state to final state. Yes, accepted. Give all the strings in this language. This finite automata is going to accept all the strings. But then you should not say that the smallest, this finite automata, let us say, call it as finite automata 2. This one doesn't accept this language, because according to the definition of acceptance of a language, a finite automata is said to accept a language if it accepts all the strings in the language, as well as it should reject all the strings which are not present in the language. But if you look at this, we are accepting all these strings in the language as well as all these strings which are not in the language. Therefore, the finite automata, this one is the exact automata or the required automata for our language and not this second one. Got it? Okay, so let's just extend this question a bit. Continue.